we have stopped today. Last two classes, we have seen some general attributes of heavy ion conditions. And in this class, we will just quickly discuss some of the signatures of Quark-Gluon plasma production in relativistic heavy ion conditions. So let's start with the space-time picture of the heavy ion condition or the stages of the heavy ion condition. So as you know that in relativistic heavy ion condition, the colliding nuclei are Lorentz contracted along the direction of the beam, that is along the z direction. So these are basically the picture of Lorentz contracted nuclei which are about to collide. So the initial state before the collision, initial state means before the collision, the distributions of nuclei, the part of quarks and gluons inside the nucleons of a nuclei are given by the Partha distribution functions. So what are Partha distribution functions? This tells you the probability of finding a parton with a given momentum fraction x inside a nucleon. That nucleon could be a free nucleon, or that nucleon could be a nucleon bound inside a nucleus. So in case of a nucleus-nucleus collision, this is basically a bound nucleon. And we talk about the parton distributions of quarks and gluons inside a bound nucleon. Okay. So and after the collision happens, in that center of the collision zone, the colliding nuclei deposit a large fraction of their kinetic energies to excite the vacuum, and a hot and dense medium is created. Because the medium is very hot, and after the scattering among the different partons inside the medium, very soon a thermalized system, thermalization is reached, and you can define, you can basically define the system or characterize the system in terms of few macroscopic variables, for example, pressure and temperature, so on and so forth. And since the pressure inside the medium is much higher compared to the vacuum, because outside the pressure, in the vacuum the pressure is very small, so the system starts expanding, and you have an expanding medium, and the initial energy density of the medium is very high. So it will expand at the same time. Along with the expansion, initially it expands as a partonic medium, and then at one point hadronization occurs, so hadrons are formed, then it still expands as a medium of hadrons, and eventually as time would reach where the mean free path of the collision will be equal to the size of the system. At this moment and beyond that moment, it is no longer possible for the particles to maintain the equilibrium because the collisions become so infrequent. So they no longer collision in the medium, rather they decouple, the particles decouple from the system and they freely stream to the detector. This is known as the final state or the freeze out state. So in the final state, there are the hadrons are formed from the fragmentation of particles, and these hadrons basically freely stream to our detector and you detect them experimentally. So this is more or less the different steps of the heavy ion collision. So if you look at the more detailed sequence of these events or of this collision, so at first and out of equilibrium, high density state is created, which expands longitudinally. Why it expands longitudinally to start with? Because the initial colliding nuclei, they do not have any transverse motion. They predominantly have a longitudinal motion. So once the medium is produced, initially the equilibrium is not yet reached, because to reach equilibrium, the constituents in the medium, they have to rescatter among themselves. Only when they have a sufficient amount of rescattering among themselves, the energy will be distributed in such a way that at a given temperature T, probability for a particle to have an energy is e to the power minus E by T. So before that, the phase is known as the pre-equilibrium phase. And this pre-equilibrium phase has a predominant motion along the Z, along the longitudinal direction, because of the inertia. Because initial colliding nuclei have predominantly moving the Z direction, and because of the inertia, to start with, the produced medium will also have a motion along expansion along the Z direction. However, sometimes this is known as the anisotropic Quark-Gluon plasma. You might have read, some of you might have heard of this. So initially, it will expand longitudinally, then equilibrium will reach such that it will have the transverse expansion will set in, and the produced system will start expanding both in longitudinal as well as in transverse direction. So as I said, the system undergoes rescattering, achieves a local thermodynamic equilibrium, and it cools and expands like a fluid. And this expansion can be described by hydrodynamic equation. So you already will have a detailed course on this hydrodynamic equation, as I see from your program. So when the temperature drops below Tc, the transition temperature, there a hadronization occurs and system makes a transition from the hadron phase, from the parton phase to the hadron phase. Then the hadron goes eventually undergoes squeeze out and the particles stream towards the detectors. So this is the another in the space-time. This is the evolution. This is the space-time evolution of the heavy-ion collision system in terms of this Minkowski diagram. It is in the terms of space-time hyperbola. So this is the time axis along along the perpendicular direction. In the horizontal direction is the z-axis. So initially, the two colliding beams in the center of this is looking being looked at the center of mass sphere. So initially, the two beams are colliding, so the collision happens at z equal to 0, and at the time scale of tau 0 is of the order of 1 Fermi by C, and equilibrium, local thermodynamic equilibrium is reached, and you have a Quark-Gluon plasma, which initially evolves as a Quark-Gluon, this Quark-Gluon plasma will eventually expand and undergoes gradual cooling. Then at a point where the temperature is of the order of Tc, which is basically the temperature, transition temperature, the hadronization occurs. After the hadronization occurs, eventually a time will come when all the inelastic scattering between the hadrons will stop. They will cease. This is known as the kinetic freeze-out. System can still expand and there may be interactions, but these interactions will be elastic interactions. What does that mean? That means elastic interactions are the interactions where new particles are produced. So in elastic interaction, many new particles are produced, whereas in an elastic interaction, then no new particle will be produced. The particle compositions are frozen at the point of your chemical freeze-out, but still particles can scatter among themselves elastically, so that their direction or their momentum might change. As a result, it will affect your PT spectra, but not the yield of the particles. Okay, the yield of the particles get freezed at the chemical freeze-out, and eventually a situation will come when the mean free path of the system will be equal to the roughly equal to the size of the order of the size of the system. Okay, size of the firewall. So no more scatterings will be possible, no more collisions will be possible, and system will system will show a kinetic freeze out or thermal freeze out, which means that their elastic collisions are no more possible. The elastic collisions also cease, and the particles will decouple from the medium. And particles will decouple from the medium, and they will reach your detector, Okay. So now question is, what are the signals, or what are ultimately what we measure in our detector is only these final state particles which reach in our detector. By measuring them, what information can we gather about the medium which formed in the collision, or how can we characterize the fireball? We can study the properties of the fireball just by measuring the particles which are registered in our detector after this kinetic freeze out. So there are different particles. There are different sorts of particles which are detected in our detector, and these different sorts of particles give us different information about the plasma which is expected to be produced in the early phase of the collision. So one is the radiation of hadrons, that you measure basically different hadrons, kaon, pion, protons, etc. So you measure their PT spectra, and this PT spectra gives you information. You measure their yield, and measurement of their yield gives you information about the chemical freeze-out temperature and chemical freeze-out barrier chemical potential. Similarly, if you measure their PT spectra, they gives you information about the kinetic freeze-out temperature and the velocity of the medium at this kinetic freeze-out point. Then, if you measure the azimuthal asymmetry of this, if you measure the azimuthal asymmetry of these hadrons, you learn about the degree of thermalization or about the collectivity of the expanding medium. If you measure the very high PT hadrons, they will give you information about the energy loss of the quarks and gluons inside the medium, which indeed is useful to estimate the density of the medium formed in the collision. And from this density, estimating the density, we understand this is a very highly dense gluonic medium which is formed in the collision, and no hadron can survive at this density. This must be a partonic medium. Then you can also study the quarkonia, the bound states of heavy quarks and antiquarks, and basically the reduction of their yield, so that there less production in heavy ion collision compared to PP collision, which is known by the name of quarkonia suppression, gives you idea about the device screening that must have happened if a plasma is produced in the collision. So we'll start with the transverse spectra of identified hadrons. I don't want to, which is useful to get information about the kinetic freeze out achieved in the heavy ion condition. As I said just now, that if you look at the yield or you measure the ratio of the yields of different hadrons, and if you analyze their yields or their ratios using a statistical model or a thermal model within the grand canonical ensemble framework, you basically get information about the chemical freeze out. Okay. So you learn what is the baryon chemical potential and the temperature at the point of chemical freeze out. But I don't want to engage in a discussion in that because Sandeep has already discussed in the best possible way. So we just skip that discussion. We will start directly from the transverse spectra of identified hadrons. So they carries information about the kinetic freeze out. So kinetic freeze out is the point where your elastic collision stops. So no more any kind of collision is possible in the media, and particles will come out. Their momentum distributions get frozen at this point, and particles will come out at this position. The kinetic freeze out temperature is basically extracted from the slope of the Pettit spectrum, and it has been seen that if there is a thermalization, then your Pettit spectra or empty spectra will have a form e to the power minus mt by t, the Boltzmann distribution. However, the t here, the inverse slope, rather not the slope, but the inverse slope of the PT or empty spectra is not the actual temperature of the medium. Why? Because you have an expanding medium. This e to the power minus mt by t or e to the power minus pt by t is valid for a static medium. But what we have a medium which is in thermal equilibrium, but at the same time it has a collective expansion velocity. That means the medium as a whole is expanding. As a result, what we have basically is the emission from a boosted thermalized source. Okay. So how do you know that? To know that you have an emission from expanding medium, you see that the Pettit spectra in A collision, which is given by the field symbols, are flatter compared to the Pettit spectra of the same hadronic species in PP collisions, which is given by these open symbols. Okay. So this flatter spectra in a heavy ion collisions compared to PP, it tells you that in AA collision, in heavy ion collisions, expanding, these particles are coming out from a medium which is expanding, which shows a collective expansion. Also, the effect is stronger for massive particles. So the red stands for pion, the blue stands for kaon, and the black stands for proton. So proton is mass of pion is less than the mass of kaon, which is even lesser than the mass of the proton. So you can see as we keep on increasing the mass, the spectra becomes more and more flattened. Okay. So this basically tells you that there is the presence of collective fireball expansion, and this is an effect of the radial effect. And in the non-relativistic limit, one can show that the slope of the Pettit spectra, you basically what you measure is T effective. So you can describe the spectra in A collision as e to the power minus Pt by T effective, or e to the power minus Mt by T effective. Okay. So this T effective is known as the effective temperature, which has the actual kinetic temperature, which is kinetic freeze out temperature, which is known by T kinetic, as well as a flow term, which is m times beta T square, where beta T is the average radial expansion velocity. It is symmetric in all directions, and is why we call it a radial expansion velocity, and m is the mass of the particle. So for that same T and same beta, because T effective and beta T, they are supposed to be the properties of the fireball, the properties of the medium. So they should be common to all particles. Okay. For T kinetic and beta T, the freeze out temperature and the beta T, they are supposed to be same, more or less to be same for all the particles, because they are the properties of the temperature or the velocity of the properties of the fireball. Whereas M will be different for different particles. Okay. So larger be the M, higher will be the T effective, so flatter will be the spectrum. And this is exactly what you see when we measure the PT spectra of hadrons in heavy ion collision and we compare them with the PP collisions. So you can have a more finer analysis or a more detailed analysis. This is basically a crude analysis where you basically assume a non-relativistic approximation. So finer details can be obtained from a model which is known as a blast wave model analysis or blast wave model. So this blast wave model is an approximate to your hydrodynamical model solutions, because in the hydrodynamics ultimately you have a time evolution of the quantities. So in blast wave you do not have that. In blast wave, what you model is the freeze-out surface. It's the surface of last scattering or the surface from where particles are being emitted. So you model the freeze-out surface, and from there you basically try to have an expression for the PT spectra or MP spectra of the emitted hadrons. So here you basically assume that the particles are emitted from a thermalized fireball moving with a common radial velocity in the transverse plane. So sometimes blast wave models are also known as the boosted thermal model. Why thermal model? Because you assume the local thermalization, and why boosted? Because you assume the medium is expanding with a common radial velocity, and the effect of this expansion or the velocity of the medium is encoded in the temperature of the emitted medium or in the PT spectra of the emitted particles. So there are different variants of the blast wave model existing in literature. You will see there is one is called Boltzmann-Gibbs blast wave model, where you start the equilibrium is described by a Maxwell-Boltzmann distribution. Then there are different versions. At high energy, the version you assume the boost invariance in longitudinal direction, so you have a boost invariant blast wave model. However, such kind of models is not these models are valid when you have a flat rapidity distribution. But at very low energies, like in the beam energy, in the lower part of the beam energy scan, or even in the upcoming FAIR or Mika experiments, you do not have this boost invariance maintained. So here your rapidity distribution is Gaussian in nature, which means it doesn't have the boost invariant symmetry, because boost invariant symmetry demands a flat rapidity distribution, or your quantities are independent of the longitudinal motion or y. Whereas at lower energies, like at GSI or FAIR or at Mika, your rapidity distribution is Gaussian, which basically tells you the breaking of this boost invariant symmetry in the longitudinal direction. So in that case, you basically have a non-boost invariant blast wave model. But anyway, here, since we are mostly discussing here the Rick and LHC results where this boost invariance is maintained, so we will discuss the outcomes of a simple Boltzmann-Gibbs boost invariant blast wave model. And here the PT spectra can be, if you do the calculation starting from the freeze-out prescription, you will ultimately reach here. You can see the PT spectra, this dN by PT dPT, which is same as dN by MT dMT. It can be written as 0 to integration of 0 to R dr MT. Then this I0 and K1 are the Bessel functions. Okay, so and this rho is known as the space-time rapidity, and it is related to your radial velocity in the transverse plane beta t, as rho is equal to tan hyperbolic inverse beta t. Okay, so this is the most commonly used version of the blast wave model, and it depicts the particle spectra at the kinetic freeze-out with mostly two physical parameters. One is T kinetic, the kinetic freeze-out temperature, and one is average of beta t, the average radial velocity. But the velocity has a profile. There are models which assume the constant value of the velocity, but most of the models they assume a profile of the space-dependent velocity, or a spatial profile in this radial velocity. So it is modeled in such a way: beta s into r small r by capital R. Capital R is the size of the firewall whole to the power n. So this is basically a power dependence. So you model it in such a way, and beta s is the surface velocity. So you model it in such a way that your velocity is general maximum at the surface, and it's basically 0 at the center. So the surface it expands more, and as you come inside and more inside to the more and more towards the center, you have a smaller velocity. Okay. So what is this n? N generally has a value n equal to either 1 or 2. So if you look at the traditional blast wave models, they basically take n equal to 1. Because this basically, if you put n equal to 1, then your velocity profile matches the Hubble expansion. Okay, which says that the system, the velocity increases as you increase the size. Okay. And then from this velocity profile, you can basically calculate you can basically calculate an average velocity beta t, which you can write as 2 star beta s. Beta s is the velocity at the surface of the firewall divided by 2 plus n. So in more recent papers in ALICE, the experimental data papers, you will see that when they measure the PT spectra of these identified pions, kaons, and protons, they also do the blast wave analysis and give a value for this T kinetic, the freeze out temperature, and the kinetic freeze out temperature, and average radial velocity. And there are basically works where this n is held as a free parameter. Now here there are 2 questions. One is, so as I said, in the blast wave, the 2 important parameters, the 2 important physical parameters is T kinetic and beta T. But we have not discussed about mu B. We have not talked about the baryon chemical potential and the kinetic freeze out. It is enough to know the freeze out, kinetic freeze out temperature and the average expansion velocity of the medium. So why are we not talking about, or why the mu B is not an important parameter for the blast wave model? Can anybody tell? Why the baryon chemical potential is not a very important parameter of the blast wave model, which basically used to describe the properties of the firewall at the kinetic freeze out. So the blast wave model is basically used, or blast wave analysis is basically to extract the kinetic freeze out parameters of the firewall. So why mu B is not very important here, because you will see, if you see the blast wave model, they always the 2 main parameters, apart from a normalization constant, the main 2 parameters which decide the shape of your spectra are T kinetic and beta T. Why not mu B? Why not baryon chemical potential? They are measuring proton. Proton is a baryon, so why not? They are not talking about. Why are they not talking about mu B, the baryon chemical potential? Priyanshi?
Sir, maybe because we are assuming local thermal equilibrium, maybe. I'm not sure about this.
Local equilibrium, but then you are defining T, right? You are defining as temperature is a parameter.
Yeah, that is correct.
Sir, I think it is because it is beyond chemical chemical freeze out, right? So yield is fixed, so we don't need to worry about.
Very good, very good. Who is that? Shapnesh. Okay, very good. Because mu B is not important, because ultimately mu B decides what? It decides the yield of your different species. It defines the yield of your different species. So mu B is frozen at the time of chemical freeze out. After that, mu B will not change, because you have only those many number of particles. What is the definition of mu B? Vedanta told in the very first class, right? It is the energy, mu B is the energy required, or the free energy required to add 1 more barrier, or to extract 1 more barrier from your 1 barrier from your system. So the now chemical composition of the system, or how many particles, which particles in how many numbers, the yield of the particles are already fixed at the point of chemical freeze out. But we are the medium has expanded further, and we are talking about the blast wave model describes the properties of the system at kinetic freeze out. That is why mu B is not important there. The mu B is already frozen at the time of chemical freeze out. Okay, very good, Sapnesh. So then there is one more question: why the model is called, or the blast wave model is called a blast wave model? Why this name is given, blast wave model? Anybody? Arushi? Arushi works with blast wave model, right? Arushi, you work in STAR?
Yes, I've studied the blast wave studied model, but I have no idea why is it named so.
I remember you gave a very good talk in the STAR ALICE collaboration meeting. You are basically you are working with Lokesh, right? You are giving this blast wave model analysis of the spectra of identified hadrons in the beam energy scan, right? I think in the 62.4.
Yes.
Okay.
Yes, 54.45.
Very good. Very good. Yeah, I remember you gave a very good talk. So now you tell why the name blast wave is given. There must be some reason, no? Why the name blast wave is given. Any idea?
No, I don't have any idea why is it named so.
Okay. Anybody else? Why the name blast wave was given? So if you generally, traditionally or generically, in the original versions of the blast wave model, if you see, the n is generally set to 1, okay, which is basically a Hubble kind of expansion. That as the source size increases, your velocity becomes bigger. Okay, so if you take that, then your beta t is beta s into r by r, right? Your velocity profile beta t is equal to beta s into small r by capital R. But what is beta t? It is the transverse velocity in the radial plane. So you can write beta t is nothing but d small r by dt, r dot d small r by dt. If you take it as dr by dt, if you write beta t is dr by dt, it is equal to beta s into small r by capital R, where beta s is a constant velocity at the surface. You will see, if you solve for r, you will see the time dependence of small r p is given by r. It basically, if you solve this equation, and get an expression for small r, you will see this will be exponentially increasing in time. Okay, this will be exponentially increasing with time, and that is why the name blast wave is given. Is it clear, Arushi? Is it clear? Okay.
Yes.
You just write. You just take 2 lines, right? To write dr by dt is equal, and then dr by r is beta s by capital R into dt. Okay, and if you do, then it will have ln r, and then r will, you see, the size will exponentially increase with time, and that is the reason the name blast wave is given. So then we can just calculate the blast wave. We can also apply the blast wave model to the data at different centralities. So this is the results for 2.76 TeV lead-lead collisions and 200 GeV gold-gold collisions. The 2.76 is from Alice experiment, and 200 GeV gold-gold is gold-gold collision is from star experiment actually. So for both the cases, what we have seen, that this beta t increases for more central collision, both at Rick and LHC, whereas T kinetic decreases with multiplicity. Because this exactly the multiplicity, the more central collisions have more multiplicity. That means beta t increases with more central collision, both at Rick and LHC, whereas the freeze-out temperature decreases with increasing multiplicity. And the similar trend is observed at Rick and LHC. What does that mean? That means more central collision have a higher velocity. Okay. And in the more central collision, you have more energy deposition. If you have more initially, you have more energy deposition, the system will expand longer in time. If the system expands longer in time, it will have at the freeze out, it will undergo late freeze out. If it undergoes less freeze out, it will have a higher velocity, because velocity will develop till that time. So it will have a higher velocity, and it will have a smaller value of T kinetic. I think the same results in the beam energy scan has already been obtained by Arushi. She gave a talk some time back. So I still remember that talk. And I don't know, many of you have already seen that. Okay. So here there is a, but how this T and beta are related? So this is the T and beta for both Alice and star, and at different centralities. Okay. So what we find that T and beta are anti-correlated. This is clear from here that if you have a smaller beta, you have a higher T, or you have a if you have a very high beta, you have a very small T, and you have a very small beta if you have a very high T. Okay, because this T and beta are anti-correlated, because ultimately both T and beta basically decide ultimately the shape of your SPT spectrum. For the same value of for a lower, you can have the same value of the slope of your spectra. You can have the same value of T effective with, if you put T high but beta small, or beta high or T small. That is why they are called anti-correlated, and this is shown by this ellipse, which basically tells you this this is the region, this defines the region of uncertainties in both T and beta. Okay, and sometimes this is called a correlation matrix, or this anti-correlation ellipse. Okay. So the average velocity is maximum in the most central collision, and for 2.76 TeV, 0 to 5% lead-lead collisions at 2.76 TeV energy of per nuclear pair, your average beta T is of the order of 0.65. Okay, and as clear from this plot, for all the centralities, T and beta are anticorrelated. You can have the same shape of spectra with high T or small beta, or the vice versa. So this is the beam energy dependence of the kinetic freeze out parameters. So this blast wave fit has been made to the invariant yields from to top rig beam energy scan as well as LSC data, and all these bulk particles, that is pion, kaon, and proton, they are simultaneously fitted with this blast wave, and the results are shown here. So get is the beam energy dependence. So as a result, you get the T and beta at different beam energies, and here it shows the beam energy dependence of the parameter T and the parameter beta. So you can, as you can see, as you go to the higher and higher collision energy, you have a stronger and stronger radial flow at higher collision energy. Why? Because if your collision energy is higher, so the fireball which is initially produced because of the collision will have higher energy density, which means it will evolve for longer time, and eventually it will have higher beta. Okay. And here, so that is why your beta shows an increasing trend with beam energy. And here there is a plot for the temperature as a function of beam energy, and there are two freeze out temperatures are plotted. One is the chemical freeze out temperature, which initially increases and then eventually saturates, and this is the kinetic freeze out temperature. Okay. So as you see that as you increase the energy, beam energy of the collision, there is an increasing difference between T kinetic and T chemical and T kinetic. So at lower energies, they are more or less same. As you go on increasing the energy, both of them get separated. Your T chemical, your chemical freeze out temperature is much higher compared to your kinetic freeze out temperature. So what is meant by that? That means by that in between there is a significant amount of time elapsed between the chemical freeze out, which should happen earlier, and the kinetic freeze out, which must have happened late in time. Because that is why in that time the medium has also cooled, and hence you have a smaller value of T kinetic compared to T chemical. So that means the rescattering in the hadronic phase becoming important as you increase the energy of the collision. Because that means because you know the chemical freeze out occurs close to your hadronization temperature, close to your transition temperature. Once the medium gets hadronized, immediately the chemical freeze out occurs. But from this chemical freeze out till kinetic freeze out, the medium has evolved significantly as you keep on increasing the energy. And that is why there is a separation between the chemical freeze out temperature and kinetic freeze out temperature. Okay, so more details, these are all crude models, and more details analysis of this yield and the spectra are basically obtained from your hydrodynamics, which is, of course, we do not have a scope to discuss that in these lectures. So now we are up till now we have been talking about the radial flow, which is symmetric in azimut, which is symmetric in phi. Now what we have come to anisotropic flow. I believe you already have a detailed discussion of anisotropic flow in the previous class, but still for the completeness, we will discuss it. So in non-central collisions, as you know, for which the impact parameter is non-zero, the overlap region of the two Lorentz contract nuclei is almond shape. It is like an almond, okay, or it is elliptic. So the emission pattern of the particles will be, for these non-central collisions, will be influenced by the interplay of two quantities, the mean free path and the system size. If the mean free path is much higher than the system size, so that means the particles will hardly collide inside the medium, or they will not experience the elliptic shape of the medium, and they will emit isotropically from the medium. However, if lambda, the mean free path characteristic mean free path of the system, is much smaller than the system size, then the particles, the constituents in the medium will be scattered among themselves significantly, which will help to establish the local thermal equilibrium. Okay, and you can describe the system in terms of relativistic hydrodynamics, and which basically predicts that if you look at this azimuthal distribution of the particles, the d and d phi will be anisotropic in nature. It will now have preferential emission on a particular along the x direction or along the direction of the impact parameter compared to the y direction, The direction along the direction of impact parameter is called the in-plane direction, and a direction perpendicular to that is called out-of-plane direction. So the particles will have a preferential emission in plane compared to the out-of-plane. Okay. So why this is so? This is because as if lambda is much smaller than r, that means there will be a significant amount of rescattering, and the system will achieve local thermal equilibrium. Once the system achieves local thermal equilibrium, you can define the system in terms of a few macroscopic variables like pressure, temperature. So the pressure gradient will not be same everywhere. Okay, the pressure inside will be much larger than the pressure outside, where it is a vacuum. The system will expand. Also, the pressure gradient along this direction, along the x direction, will be larger than the pressure along the y direction. Why? Because along the x direction, the elongation, the size of the system is smaller because of its anisotropic shape. The system size is not same along x and along y. So there is the system size along x. The system is more contracted along x direction compared to the y direction, which means the pressure gradient will be more because your dp dx, if p denotes the pressure, so the dp dx will be greater than dp dy. So you have more pressure. The system will, the particles which are coming out from the system, they will feel more pressure gradient along x direction compared to the pressure gradient along y direction. That means this initial state anisotropy and the anisotropic pressure gradient will convert the initial state special anisotropy into final state momentum anisotropy, meaning that the more particles, because of the larger pressure gradient, more particles will be emitted along the x direction compared to the particles along the y direction. So what will be the outcome? The outcome of this will have, they will have an anisotropic emission pattern in D and D5. Their azimuthal distribution will no longer be isotropic, that it will be highly anisotropic, with more particles along x and less particles along y. And this anisotropic pressure gradient.
So when you say this local thermal equilibrium, it means length scale in space coordinate, right?
Yeah.
What do you mean by that? So
local thermal equilibrium, by local thermal equilibrium in the simplest sense, by local thermal equilibrium we mean that your temperature or pressure or your thermodynamic quantities are as a function of space and time, because you have initially a very anisotropic medium which collides, which have, or because of your initial density distribution. The density distribution inside the nucleus, it's like a wood section distribution, which means you have more nucleus, more matter towards the center and less towards the periphery. Okay, so the distribution itself, after the fireball is produced after the collision, your matter distribution will be highly non-uniform. You have a core and you have a corona. In the core you have more matter, in the corona you have less amount of matter. Also, it is an expanding medium. So together they mean this non-homogeneous and non-homogeneous spatial density, inhomogeneous spatial density, and it is an expanding medium. Together they mean that your thermodynamic quantities like pressure or temperature, they are a function of space and time, x and time. So that is what is precisely the outcome of your local thermal equilibrium. Which in
okay, but
words,
still we can extract T kinetic as a single temperature, right? From the previous slides, so you use blast wave and
yes, because this is a very good question actually. So because you do it, because otherwise how many temperatures, then this T kinetic basically tells you some average. This T kinetic tells you some average. Okay. And there are two things. One is that since you are this T kinetic, you are extracting this T kinetic at the freeze out. So initially the momentum will be extremely inhomogeneous, but then as the system expands, that means more matter is transported in. To start with, you have more contraction along the x direction and more elongation along the y direction. But as the system expands, and because of the pressure gradient, you have more matter transported along the x direction compared to that in y direction. Or their system will try to isotropize itself. This is number one. And number two is that at the freeze out, you already have a very dilute system, right? Where the collisions have become so infrequent that you are reaching with a freeze out. Okay, that is, I think, the reason why you still characterize the system with a single kinetic freeze out temperature. But you are right. Initially, since we talk about a local thermodynamic equilibrium, that means we have many fluid cells inside the fireball, which basically undergoes freeze out at different times. Since it is local, they undergo freeze out. They should have undergone freeze out at different time. Okay, but that if you want to do that, your analysis will be extremely difficult. So what you basically get, your average beta T or T kinety, they in some sense they represent some average properties of the system.
Okay.
Okay.
Another
Similarly,
thing is, so
just a moment. Similarly, for your hydrodynamics, when you give as an input, one of the inputs, as you know, is the thermalization time or the QGP formation time. You give it as an input, but generally you give only one value of tau zero, even though you know that hydrodynamics resides on the assumption of local thermal equilibrium. You generally give one single value of tau zero, isn't it?
yes.
Okay.
So the other question is, so on this almond-shaped reaction zone, so you said in the final state we'll have a anisotropic emission of particles, right? So that emission, so that emission is in the coordinate space, but how anisotropic emission of particles is still sounds like in coordinate space, right? How is it
I said
in the
anisotropic emission? No, the anisotropy itself is converted from the coordinate space to the momentum space because of this anisotropic pressure gradient. The anisotropy there needs to start with, there is anisotropy in the coordinate space, and there is a local thermal equilibrium which leads to anisotropic pressure gradient. So this anisotropic pressure gradient converts the initial special anisotropy. It converts it into the anisotropy in the momentum space anisotropy, which is basically is your measure. V2 is the measure of your or V2 or elliptic flow coefficient, or V2 is the measure of your anisotropy in the momentum space. So it is not only anisotropic special anisotropy is sufficient. It is a necessary condition, but it is not a sufficient condition to have the V2. In addition to your anisotropy in the space, in the coordinate space, you also have to have the anisotropic pressure gradient. And this pressure gradient can only be, the pressure itself can only be established when your local thermodynamic equilibrium is achieved. And your local thermal equilibrium is achieved when you have a sufficient number of rescatterings among the constituents of the medium. So this is the anisotropic pressure gradient, which converts your initial special anisotropy to your momentum anisotropy, which is basically characterized by the elliptic flow, so that you have a more preferential emission, you have more particles emitted along the x direction compared to your y direction.
So this preference is in momentum space.
Ultimately,
final state emissions,
they are in the momentum. Because ultimately, how do you look at this phi? This phi is azimuthal angle. So how do you measure this phi, Devashish, in experiment?
I have not measured it, but it sounds like the reaction plane angle, right? The psi, the phi.
No, this is not reaction plane. This is the emission angle of the particle.
This is the phi. So this is tan inverse Py by Px, right?
Exactly. So how do you measure it? You measure it in terms of Py by Ps. You don't do it y by x. You do it Py by Px. Okay, that means you measure this phi in terms of your momentum coordinates, momentum variable.
Okay, so it means anisotropic emission of particles in the momentum. Okay, thank you. Yeah. Okay.
Okay, so there are certain properties of V2. First, it is sensitive to the early stages of the collision, and it is maximum for the mid-central collision. So both arguments for both of these statements we can just, if we expand what Devashish has now told, based on his arguments, we can basically I can try to I convince you for both of these statements, because you see initially the state is anisotropic, highly anisotropic in the space. Okay, and then there is an anisotropic pressure gradient which converts initial state spatial anisotropy to the momentum space anisotropy. And then more particles are transported along the x direction compared to the y direction. As a result, because of there is anisotropic pressure gradient and there is an expansion rate is faster along x compared to y, the system is more elongated along y compared to x, and the system has a faster expansion along x than in y, system will try to become more and more isotropic. As the time passes by, system will try to become more and more isotropic. And as soon as system will tries to become more and more isotropic, the V2 will be smaller and smaller. So if you plot V2 as a function of time, you will say at the very instant when the collision occurs, V2 will be very close to 0. Then in the initial time, it will have a peak, and then as the time passes by, V2 will again diminish. Okay? Which basically tells that V2 is sensitive to the early stages of the collision when your firewall is highly anisotropic. Also, another thing is that V2 is maximum for mid-central collision. It is also small for pure central collision. It is also small for pure peripheral collision. Why? Because in the pure central collision, your firewall of the overlap dome is highly symmetric, and V2 is initially generated because of the initial state spatial anisotropy. That is the reason V2 is very small in central collision. But what happens to the peripheral collision? They are highly anisotropic. They are more anisotropic. Their spatial anisotropy is even higher compared to your mid-central collision. However, there you do not have the enough number of risk scatterings because the number of participants in a peripheral collision is very low. Okay, so there are not enough number of risk scatterings among the produced particles. Unless there are enough number of risk scatterings, the degree of thermalization is not very high. If that is the case, your pressure itself will also be low, so will be your pressure gradients. That is why V2 is also small for peripheral collision. And that is the reason that not only initial state spatial anisotropy is not the only reason for generation of V2. You need the initial state spatial anisotropy. At the same time, you need a high degree of thermalization, which will lead to an anisotropic pressure gradient, which in turn convert your initial state spatial anisotropy to final state your momentum anisotropy, which is characterized by V2. So thank you, Devashish, for pointing this out.
Thank you, sir. Thank you for explaining.
Okay. I hope this is clear.
Yes, to me, yes.
Okay. So as I said, V2 basically characterizes the strength of the elliptic flow. At RIG, V2 of identity, V2 has been measured both at RIG as well as at LHC. At RIG, what has been found is that V2 of the identified at low VT, V2 of identified hadrons increases with VT, and it shows a clear mass ordering. What is meant by mass ordering? VT of pions is more massive with the particles, smaller will be its V2. So pions having the lowest mass hadrons, they have the largest V2, and then as you keep on increasing the mass of the particles, their V2 is decreasing. This is what is predicted by hydrodynamics. So that is why this is known as sometimes it's called hydrodynamic mass ordering, or the generation of V2 or exhibition of V2 in data is hydrodynamic in origin. This is the signature of the collectivity, that the medium as a whole is expanding. However, at higher P2, what we see beyond QGP, what we have seen, there is a departure from the hydrodynamic behavior. This mass ordering is broken at high PT, and what we see that there is a separation between baryon V2 and meson V2 are separated into two branches. Okay, they are separated into two. They are being separated into separate groups. This is known as the breaking of the mass ordering. And what could be the reason of that? The reason as is being thought is that the reason for breaking of this mass ordering is that the particle production mechanism at PT greater than 2 GeV is something else. Okay, so this is not just a thermal production of particles, which is the case for a thermalized medium. So the hydrodynamic descriptions, the application of hydrodynamics is based on the assumption of the medium has achieved local thermal equilibrium. This is valid for particles up to some PT of the order of 2 to 3 GeV. And beyond that, this hydrodynamic mass ordering breaks, and some different production of particle production mechanism comes into play here. This is known as quark coalescence. And this similar behavior of V2, like at low PT you see hydrodynamic mass ordering, and at high PT this mass ordering gets broken and you see baryon meson crossing. So the similar behavior is observed also at LHC. Okay, here this is the data for 200 GeV gold-gold collision, and here it is the data for 5.02 TeV lead-lead collisions. So we will now take a closer look at this intermediate PT at intermediate V2 or PT at intermediate V2 at intermediate PT. So this V2, when expressed as a function of PT or rapidity, this is known as the differential elliptic flow. Okay, when you plot V2 PT as a function of PT, this is known as the differential elliptic flow. Okay. So what has been shown here, as I said, that at the PT where 2 GeV, this V2 of baryons and mesons, the hydrodynamic mass ordering is broken, and V2 of baryons and mesons, they get separated into two branches. However, once you divide this V2 by NQ, where NQ is the number of constituent quarks in that hadron, and plot it as a function of PT by NQ, then all of them fall one on the other. So this value of NQ will be 2 for mesons because they are Q-cuber states. The number of constituent quarks are 2, and for baryons this will be 3 because it is Q state. Okay, so if you divide the baryon V2 by 3 and plot it as PT by 3, and meson V2 by 2 and plot it as a function of PT by 2, PT by NQ, you will see that for all the particles V2 of them will fall one over the other. So this basically tells you this quark coalescence or quark recombination is the characteristic mechanism for hadron production in QGP. This phenomenon is known as constituent quark number scaling, and this basically tells you the collectivity of the V2 which you observe in the data. They must have originated in the partonic phase, not in the hadronic phase, but in partonic phase or in the QGP phase. Or whatever collectivity you observe in your data at RIC or at LHC, they are partonic in origin. That is why they have a common value, because in the partonic phase you do not know which quark is going to form in a later stage meson, which quark is going to combine with two other quarks to form a baryon at a later stage. So there the medium, the V2 will be same for each other. Only when they just combine, then one of them are falling, some of the quarks are forming baryon, some of the quarks are forming meson. So there is a model called recombination model or coalescence model, which basically of hadronization, which basically tells you that the nearest quarks which are close to each other, which are close both in momentum space and in coordinate space, which are very close to each other in position, and the relative momentum between them is small, they just combine to produce the hadrons. This is known as the recombination model or coalescence model of hadron production. And according to this model, one can show the V2 of mesons can be written as 2 times the V2 of quarks, and V2 of baryons is just 3 times the V2 of quarks. Okay. So V2, in other words, the elliptic flow of baryons and mesons are scaled to the number of constituent quarks, and this V2 of quarks as a function of PT show an universal behavior, because quarks are quarks, partons are partons. Or there is so this observation of this NC2 scaling in data both at RIC is considered as a success of this recombination model. However, this model has one very big criticism, is that this model do not account for gluons. Okay, these only talk about quarks, but we do not account for gluons, which are the carrier of strong interaction. So at top RIC energy, what is the scenario in the data? So in the top RIC energy, NCQ scaling observed for pion, kaon, proton in central and mid-central collision, which basically tells us that indicates the observed collectivity is partonic in origin. However, there is a clear departure from the NCQ scaling in peripheral collisions for PT greater than 1.3 GeV by C. We do not see the NCQ scaling, and scaling do not work at very high PT. So the reason For breaking of scaling at very high PT maybe, there is a different mechanism of particle production. Take a different mechanism of particle production takes into place, namely the fragmentation. There is called jet production of jets. So their formation of hadrons is from the fragmentation of very highly energetic quarks or gluons. This is known as fragmentation. That LHC, the scaling behavior has been observed, but that is more or less approximated. That is not as exact as this has been observed at RIC. So this is about V2. So what about the higher order harmonics? So as Sandeep has beautifully explained, so these higher order Fourier coefficients, they primarily originate from the initial state geometrical fluctuations. So if you know that the initial distributions are not smooth as described by the section distribution, you do not have a smooth distribution of nucleus. Rather, they will show some they have in the position of the nucleus have the intrinsic quantum fluctuation just because of your uncertainty principle. And because of that, this initial state fluctuations are the reason to generation of this higher order Fourier coefficients. And there are limited number of participants in the colliding zone is limited. So there is event by event fluctuation in nucleon position and their distribution. And because of this presence of this hydrodynamic expansion, this initial state fluctuations are converted to momentum anisotropies, and which basically lead to the observed higher order harmonics. And there is a striking agreement between the viscous hydrodynamic model calculations with fluctuating initial states and the data collected at RIC. So with this viscous hydrodynamics model calculations, which I believe you will listen more in Victor's lectures, they reproduce the flow harmonics V and PT for n equal to starting from 1, which is directed flow, up to n equal to 5 by viscous hydrodynamic model. And this viscous, one of the parameters of this viscous hydrodynamic model is eta by S, ratio of viscosity to entropy ratio. And the comparison of the model to data basically tells you the eta by S is very low. It's of the order of 0.12 or 0.2, which is very close to the theoretical lower bound of 1 by 4 pi. Similar results have been observed at LHC, which ultimately tells you that nearly non-viscous fluid with very small mean free path or large cross section in the fluid is being produced both at RIC and LHC. This is like a perfect fluid. So this, so the QGP which is produced in at RIC or at LHC behaves more like a liquid than like a gas. That is why sometimes this is called as a strongly coupled Quark-Gluon plasma or a strongly coupled SQGP or strongly coupled Quark-Gluon plasma. Initially, it was thought that the medium produced in heavy ion the Quark-Gluon plasma behaves like a gas. But then, but a gas will not have a large collectivity or large flow. So the data of had the different flow harmonics starting from n equal to 1 to n equal to 5. Those which are collected at RIC or at LHC tells us that the medium which is formed is more like a liquid than like a gas. And in liquid is of course gas and liquid both are fluid, but the difference is in liquid there is a strong coupling. In other words, how do you measure the coupling? So for a plasma, for example, if you consider an electrical plasma, so the potential energy goes up is E squared by R. Okay, and the kinetic energy at a temperature T is of the order of kT. Okay, R is the interparticle separation. So so one can define a parameter gamma, which is the ratio of the potential energy and kinetic energy. So more and more will be the strongly coupled medium, higher and higher will be the value of the gamma. Okay, because temperature or the kinetic energy will attribute a random thermal motion. The system will deviate from the collectivity. Whereas more liquid-like behavior is that the collective behavior wins over the random thermal behavior. Particles are not moving here and there at random. Rather, all of them collectively show a common behavior. That means we basically show the existence of a common velocity field for all the particles. So the data also supports that. So as I said, applied to RIC and LHC, more sophisticated, nearly non-viscous fluid at small mean free path, and this basically means if you have a higher collectivity, means have a higher degree of thermalization, which means there is a large number of scatterings among the constituents, which is possible if there is a large cross section for this particle interaction inside the fluid, and which of course also indeed tells you have a large mean free path. because lambda goes as 1 by n sigma, the mean frequency lambda. So there is a more sophisticated analysis known as Bayesian parameter estimation, where it is kind of a multi-parameter fit, where you do not fit a particular observable, you fit many observables together simultaneously with a multi-parameter fit. So this is one of the state of the art in your QGP analysis, and this Bayesian parameter estimation has been applied to extract the QGP properties and constant the initial condition. And once this is applied to RIC and LHC data, one has been able to extract the temperature dependence of shear and bulk viscosity. So this V2 or the anisotropic flow or the higher order flow harmonics, that or also the PD spectra, they gives us information about the collectivity of the medium. That the medium shows collectivity, which is one of the essential properties of the plasma. Also, another important point is to know what initial temperature of the plasma. So for that, because hadrons are no good to measure the initial temperature of the plasma. Why? Because hadrons come out of the medium only at the kinetic result. So the electromagnetic probes like photons and dielectrons are considered as an excellent tool to find the temperature or the early phase temperature of the fireballs. So photons are basically the penetrating probes. They are produced in the all stage of the collision, and then they can be used to study the space-time evolution of the fireball. So PT distribution of the direct photons, the photons what to measure in your experiment, they are known as inclusive photons, and they can be divided into two categories. One is called direct photons, and one is called decay photons. So decay photons are not interesting. Decay photons are mostly the photons which come from the decay of pi zero going to gamma gamma. So they are basically background. But what is more interesting to us are the direct photons. There are different categories of direct photons also, but let's not go into that. So it has been shown by theoretical analysis that at low PT less than 4 GeV, they are in heavy ion collision, there could be an enhancement of this low photons, and this is because of the directly thermal radiation from the QGP. Photons are directly radiated from a thermalized QGP. Photons will directly be radiated. And this photon will increase the yield of the photons at low PT in AA collision, in nuclear heavy ion collisions compared to proton-proton collision. However, since the medium is an expanding medium, so the PT spectra will be affected by the velocity or the expansion velocity of the medium. So the extracted temperature will be blue shifted. It will not be the actual temperature, but will be the effective temperature of the medium. But we know how the T effective and T original, the T actual are connected. So the T effective, which you directly extract from the PT spectra for 200 dB gold-gold collision actually, this has come. This is because LHC, the value is 300 dB. So this is the effective temperature from where you can calculate the actual temperature. But this temperature, what we calculate is because photons are emitted in all stages of collision. So this is basically average over the space-time evolution of the fireball. So comparing with some model calculations, you can calculate the initial temperature both at RIC and LHC, and you can see that the initial temperature in the most central collisions at RIC is as high as 500 to 600 dB, which is much larger than the value of TC, where TC is only 116 dB of the order of. That means the initial temperature produced in the most central collisions at LHC or at RIC is much higher than the critical temperature required for the plasma production. However, since the small have a small anisotrope, because initially it will for the anisotropy to develop, it needs a certain time for the anisotropy to develop. However, what has been observed at data that there is a sizable amount of V2 as well as V3, the elliptic flow and the triangular flow of direct photons compared to hadron V2 both at RIC and LHC. Till date, there is no single hydrodynamic model which can satisfactorily explain both the yield or the PT spectra of these photons as well as the V2 of these photons. So this is known as the direct photon puzzle. But none of the models have so far become successful to describe both. So there are, on the experimental side, people are working to reduce the uncertainties in the measurement. You can reduce there are different techniques to reduce the systematic uncertainties. And on the theory side, people are trying to work, trying to find out more novel ideas or more novel ideas to include new mechanisms which could or to do new or to apply new tricks in your model, so that the model become able to simultaneously describe the spectra as well as V2 or the flow coefficients V2 and V3 of the photons. So I have not discussed here dileptons. So it's like photons. Another important signal are dileptons, the E plus E minus or mu plus mu minus square. So there is an added advantage of dilepton measurement compared to the photon measurement, and the advantage is like this. For dileptons, in addition to the PD spectra, you can also measure their invariant mass distribution. For the photons, their rest mass is 0. But for the dilepton, you can measure the invariant mass distribution of the pair. Okay? And invariant, what is the advantage of this measurement of invariant mass? The invariant mass being actually this invariant mass is nothing but a mass. So by construction, this invariant mass is Lorentz invariant. And if it is a Lorentz invariant quantity, it will not be affected by the velocity of the source or the expansion velocity of the source. So directly from the invariant mass spectra of dileptons, one can directly extract the temperature of the fireball. So that temperature is not blue shifted. That will not be affected by the velocity of the medium, which is the case for the PT spectra of photons as well as for dileptons. This is true also for hadrons. The PT spectra are always affected by the expansion of the source, but that is not true for the invariant mass of the dilepton. So in addition to the PT spectra, you have additional handle for dileptons, which is the mass. So you measure both the mass and the PT spectra of dileptons, and it has been shown by theoretical argument that in the intermediate mass region between 1 to 3 GeV, the invariant mass distribution of the dilepton is highly sensitive, or this is dominated by the thermal emission of T2 E plus E minus or mu plus mu minus square from a Quark-Gluon plasma. So measuring the thermal dileptons, you can have the idea about the source temperature of the fireball. So another thing, how much time do we have, Siddharth? Do I have?
Partha, we are almost done. So maybe quickly you can just go through your slides. I think that would be better.
Okay.
Let's say 10 minutes.
Okay. So in that case, I am afraid because I have two more things to discuss. One is called jet quenching. I just discussed them very qualitatively. So jet quenching is what? So as you know that in heavy ion collision, the lifetime of the produced medium is extremely small. So you cannot have any external flow. So, but still you can do a fireball tomography by measuring the highly energetic particles produced in the initial parton scattering. These high PT partons traverse they are called jets. Now, in case of heavy ion collision, these high PT partons traverse the medium and they lose energy. And these high PT partons fragment into narrow spray of hadrons. They are called jets. Now, in case of a heavy ion collision, these partons they lose energy due to their interaction in the medium. So, more larger and larger will be the path they travel, the distance they travel inside the medium. More and more will be their path inside the medium. More will be the interaction of the partons with the medium. More will they lose energy. And there are two kinds of energy loss. One is called the collisional energy loss, and another is called the radiative energy loss. So radiative energy loss is basically the gluon radiation, and the collisional energy loss is basically because of due to the elastic scattering between the primary parton and the medium partons, and then it basically scales linearly with path rate. So what has been observed in data that in PP collisions there are two collinear back-to-back jets. And this why there is a collinear back-to-back because of the momentum conservation, clearly observed. However, in AA collisions, only one of the jets is significantly suppressed. The near side jet is not is observed, but the other side jet is not observed. This phenomena is called as jet quenching. So this jet quenching, to characterize the jet quenching, the jet quenching is measured in terms of an observable known as nuclear modification factor, or RAA. This RAA is the ratio of the yield of these jets, of the jet particle, of the hadrons, IPT hadrons, In AA collision, divided by the production cross-section in PB collision scales with the number of binary collisions. So this number of binary collisions we calculate from the Glauber model. Had the nucleus collision been just an incoherent sum of many nuclear collision, it would be the case that no secondary medium, high density medium is produced in heavy ion collision. It is just independent sum of many nuclear collisions. In that case, your RA will be 1, because in that case your denominator scale with number of binary collisions will be exactly similar to the numerator. But if there is a medium is produced, then your RAA will not be equal to 1. And if RAA is less than 1, which means in AA collision, the production yield is smaller compared to the scale production yield of PP collision, this basically means suppression. So this jet quenching is quantified by this nuclear modification factor RAA, which is the ratio of the normalized single particle yields in PP and AA collision. And as I said, if RA is 1, there is no medium suppression. And if RA is less than 1, this indicates medium induced suppression. So RAA as a function of PT has been measured by Phoenix at RIC for various particle species. And what we see that at high PT, a strong suppression for light hadron production is observed for the first time, which is the first indication of jet quenching. Whereas RA value of direct photons, which are not affected, photons being electromagnetic in nature, they are not affected by the strong interaction. So the array of direct photons is consistent with unity. So that because photons are unaffected by the strong force. The suppression is also visible from the two particle azimuthal correlation. If you plot the delta phi of two particle correlation, in PP collision you will see one peak at delta phi equal to 0 and other peak at delta phi equal to pi 180 degree. Okay, the delta phi equal to 0 peak is called the near side peak, and delta phi equal to at 180 degree the peak is called the avar side peak. You will see that for PP collision the peak height for both near and avar side peak are more or less same. Whereas for A collision you will see the avar side peak is highly suppressed. And the avar side peak basically indicates this corresponds to the particles which traverse a larger path length inside the medium, and that means while traversing they all get suppressed in the medium because of the energy loss of the highly energetic quarks of the highly energetic partons inside the medium. So ultimately this results to a significant energy loss of partons in the hot and dense medium, and this directly indicates the formation of Quark-Gluon plasma. So what we have seen at LHC we have seen the similar suppression in RA, also confirmed at LHC with wider PT range. Because of higher energy, you can go to much higher PT range and with a better precision. And we are also able to investigate the heavy RA for the heavy flavor hadrons, and suppression is similar to the light hadrons at high PT. And results when compared with the theoretical models, this allow us to extract the medium property, the some transport properties of the medium, like you had, which basically signifies the energy loss per unit square of the momentum transfer in an elastic interaction per unit path length. Ultimately, what you basically the extracted Q hat values are much higher for both at RIC and LHC compared to what is the case for cold nuclear matter. For cold nuclear matter, this Q hat value basically you extract from the PA conditions, from the data measured in PA conditions. Ultimately, all this together basically indicates that the created matter is extremely dense, opaque, and partonic in nature, or a Quark-Gluon plasma is produced in this energetic heavy ion collisions at RIC and LHC. So there is one final thing which I don't know I have time to discuss. So I think I would skip this Quark-Gluon and heavy ion collision. This was my last signal, which is basically indication of this Quark-Gluon in heavy ion collision, Quark-Gluon suppression in heavy ion collision, the Charmonia suppression in heavy ion collision. This is also a signal which is a direct signal of device screening, because as you know, the essential properties of plasma, one is the collectivity, and another is the device screening. So the collectivity is already established by your higher order. You have this elliptic and higher order flows, and then that the medium is partonic in nature. That is a plasma made up of quark and gluons. This has been already been exhibited by observation of jet quenching. And finally, that the device screening, a color device screening is being observed. This is being this becomes clear once one look at this observable called Quark-Gluon suppression. So I don't think, Siddharth, I will have time to discuss this Quark-Gluon suppression because I have a few 4-5 slides. So what I can do, I can stop here, and then once I finalize the slides, I will share it with you. So once you upload it, the students can have a look at the slides and they can get back to me anytime they want. Will that be fine?
I think this is the reasonable approach, Partha. I think this is, yeah, otherwise, yeah. We are already half an hour late, so yeah, I think this is fine.
And if the students have any question, so they are free to ask. If you do not feel like asking now, you are always free to send me a mail. If you want, you can always free to send me a mail.
May I ask one question?
Yes, please.
So as you mentioned in this jet quenching thing, one can also observe this jet quenching by studying this two particle correlation in delta phi, where you have mentioned that in presence of medium, we expect a suppression for abside jet.
Right.
So if I understand correctly, then this abside jet is basically mostly produced from the initial hard scattering, that is the back-to-back. So my question is, means what is the why we also see a correlation in the near side, and why we do not expect any effect of this near side correlation at delta phi equal to 0 in presence of QGP?
Yeah. Okay. So I don't have that figure. Generally, what it is assumed that this depends, the amount of suppression, it depends on the amount of path length traversed by these two back-to-back jets inside the medium. Now, suppose the jet is produced close to the boundary of your medium, close to the periphery of the firewall. And if they have to traverse back-to-back, then one will traverse a much smaller distance compared to the other. Since they are back-to-back, one will just emit. Once it is produced, it will just emit from the medium. On the other hand, the other one basically traverse the entire medium. Sorry, I can't draw it here. So if it is not produced at the center, but it is produced close to some periphery, and if there are two back-to-back because of the momentum conservation, so one will traverse, the one coming at 0 degree will basically traverse a very small distance inside the medium, whereas the other one traverses a large distance inside the medium. So the path length traversed by the one which the jet for which the path length traverses more, it will lose more energy, and that is why you see a suppression for that, and you will not see for the near side one.
For the away side, it is clear to me, but for the near side, I did not understand it yet. Means the first question is why we expect this near side correlation. The
correlation you see because of their production mechanism, right? The way I understand. Maybe Siddharth can also comment, because this is a highly energetic parton which are basically fragmented into your hadrons, which you are measuring. So they are all inside a very small cone.
Okay.
Yeah, Partha, you are right. The correlation will be there in both the sides, both the away side and near side jets. But for the away side, it is more likely the correlation will be a little bit destroyed because of the medium. If you look at the triggered particle, two particle correlation in the delta phi direction, with respect to the trigger particle, let us say. So the away side, this correlation will be a little bit washed out because of the presence of medium. And in the near side, the correlation will still be present because this is basically related to the surface bias. The way you define this, when you select this near side jet, by definition, you are selecting the highest PT track in as a trigger track. So by that definition, you are biased to the surface, to the jets which are produced near the surface. So this near side, you will see less kind of effect of the medium. But if some jets are selected, let's say in the center of the jets, then center of the fireball, then both jets will see similar kind of medium effect.
Right.
Mostly this is surface bias because of the technique we used.
Okay.
Because if you just look at the photon tag jets, then you don't know the away side jets where it is produced. So then all jets are basically will show some kind of effects.
Okay. Thanks.
It seems that there are no more questions. So shall I answer that?
Yes, Partha. Thanks a lot, Partha, for finding time and giving these 4 lectures.